Okay, I'll start. Yeah, today I will start covering logic fundamentals, just a recap of logic. So some of you who might have taken a logic course may find this thing, the topic a bit familiar, and you might also seen, but nonetheless, I want to cover so that for the benefit of those that have not had a formal logic course, as well as for others, so that we, as far as notations and some concepts are concerned, so maybe it will be useful to get a refresher. So, as always, please stop me whenever you have any questions. Yeah, so why logic? Okay, as I have pointed out, we will be the model checking and static analysis methods have their basis in logic. Even more specifically, as we've already seen, all those techniques, the one step is to model the software as logical formulas, okay, both the program semantics, like the transition system model that we have seen. So those will be represented symbolically as formulas, okay? So you've already seen that, for example, an assignment statement x is equal to x plus 1 or y is equal to 2x will be represented as a relation between the value that x can take prior to the assignment related to the post-assignment. And the assertions that represent the specification that we want to verify are also converted into logical formulas. Okay, and then our techniques, as I've said in the last class, also can then be considered as within the framework of logical reasoning. Okay, so that is, you derive a proof of that the specification follows as a consequence of your model, which is represented as a formula within the logic that you use to model the whole thing. Of course, our stress will be on automation. So this logical reasoning, will be this our aim is to do it as automatically as possible, for which we will also see how certain decisions about formulas in these logics, the logic that we will be that I'll be recapping, what techniques are available to automate that. We will be discussing specifically propositional logic and its automatic procedures called SAT solvers, as well as predicate logic with various theories, and for which we will be using tools called SMT solvers. Now, this course is, you can pretty much use those automatic tools that automate logical reasoning in these logics as black boxes. We will be studying how most of the course will be on studying how how programs and its semantics can be modeled using these logics, and how these techniques, the automated reasoning of the logical, in these logics can then be used to check the specifications, but still it would be useful to know a little bit about how these automatic techniques that automate the logical reasoning within those logics work, what their strengths are, what their weaknesses are, and what the state of the art is. And that is also I will cover as part of this logical recap. Okay. Yeah. So another thing, as you can see, I mean, just to re-emphasize the same point, you've already seen that one of the, a transition system model that we used as one of the ways to model the semantics of programs and program semantics is already, as you can see, is represented. The transition relation is represented in this case as a formula. Okay, and you'll see that when the techniques for analyzing these traces will then, that they do not result in error, that the error state is not reachable in any of these execution traces, will be expressed as something that we need to prove within that logic, so that the task of verification can then be expressed, can then be implemented using these automatic reasoning techniques that are implemented in these boxes that we will be talking about, SAT solvers and SMT solvers. This is, the next 2-3 lectures will be, will expose you to the basics of logic and the techniques, automatic techniques, techniques for automating reasoning within these, within propositional logic and predicate logic. Okay, so, just like, a logic has, any logic, when it is introduced, has 3 components. One is a syntax, the syntactic rules which specify how the formulas in that logic and its various components are constructed. And then there is semantic rules, okay, for the logic that defines, gives meaning to the formulas. More specifically, when you can consider the formulas to be, which formulas can be considered to be true and which formulas are false, okay? And then the third component will be the rules to derive the deductive reasoning, the logical reasoning, which are expressed as some inference rules that can be used to derive the derive proofs in them, and to which we are adding those deductions can be automated, and what kinds of techniques are there to automate. Okay. Now, just like you saw, I mean, you already saw how, and this is the same kind of concept that we used in order to model program semantics. There were syntax for program, and then the semantics, the execution, the set of execution traces were then modeled. We saw how that could be modeled. As a matter of fact, the program semantics that I introduced to you is inspired by how a logic and its semantics is defined. Okay, and first, just like in so we introduce valuations. Okay, so since formulas in general in a logic are constructed out of variables, and the truth value of formulas in a logic in general depend on the what values are given, assigned to the various variables. So just like you saw, we used the environment object for program semantics. There is, you need to specify a valuation for the variables, which is defined as a mapping sigma of variables to the values drawn from the domain that the variables in the logic range over. So, so we have, in our case, variables ranging over Boolean. And say, for example, you could have things ranging over numbers and so on. So that is, we have the substitution, which I introduce a function that and then given a sigma, a mapping, we define the, we already saw a substitution or an update function for which updates a single variable of a map to create a new evaluation, okay, for the variables. So first we'll do in this class, I'll talk about propositional logic, maybe today and in the next class, and we'll also cover predicate logic, through logics that we'll be using to in the course for software analysis. Okay.
Sir, what do the T and the inverted T symbols mean?
Yeah, they're just constants. Okay, so we will, so the exact meaning we'll give later. So that is used for true or false. Okay, I'm just using it, the T for true and the bottom symbol for false. Okay, so
okay.
So you could use true, false. Okay, maybe sometimes I use it interchangeably, but they meant to denote true and false. Yeah.
Yeah.
Because you could have a logic in which there are no constant symbols, okay? But I'm starting with defining the logic to include constant symbols for true and false, okay? So P is a propositional variable. Okay, I call it a propositional variable because in propositional logic, every variable has to be, can only take one of these two values, true or false. And then all the logical connectives, starting with negation, conjunction, disjunction, logical implication, equivalence, and the exclusive OR operator. So, yeah, and then we have a set of atomic propositions. Okay. Propositional. Okay, so that is anything that is constructed using these grammars. Using this grammar is a well-formed propositional formula. So now we give meaning. Okay, and sometimes this meaning is also called interpretation to each of the formulas constructed as per this syntax. That is, for every well-formed formula constructed as per the syntax. So given a formula phi containing some atomic propositional variables, okay, atoms, which are in atoms of phi, and evaluation for those variables, atomic propositions, we assign, atom of phi to true and false. Okay, so yes, this true and false that I've described as true and false are the actual truth value, whereas the top and bottom here are specific constants that I choose to include in my language. Okay, this true or false is the semantic. Okay, it's a logical truth and logical false that is which will be associated with every well-formed formula. Okay, so technically, we make a distinction between the syntactic object constant T and bottom, distinct from true and false. But of course, the meaning that in the semantics that we give for T is true, that's always true, and bottom is false. So that formula T is always true and the bottom is always false. Okay, is that clear? Okay. So the truth value of the atomic proposition, which is constructed from a propositional variable P, of course, it depends on, it can be either true or false. It can depend on what your, the valuation, sigma, in which you are interpreting that formula. So that in this case, P. So it's whatever sigma evaluates P2. Okay, so if it is assigned true in the valuation, it's true. Otherwise, it's false, okay, as you'd expect. Okay, so and the rest is the meanings of the various other logical connectives are defined inductively, that is recursively, based on the structure of the formula in terms of the truth value for the formula. Okay, so this double turn style should be interpreted as giving a meaning to the syntactic, that the formula that is enclosed within the turn style for a given valuation. Okay, so that's how it should be read. So the semantics, the interpretation of not of phi1 in given a sigma is true if the interpretation for phi1 is false. If that is false, then not of phi1 will be true, and vice versa. Okay, phi1 and the formula phi1 and phi2 will be assigned true if both the interpretation for phi1 as well as phi2 in sigma is true. If either of them is false, then it will be given the truth value false. Similarly, all the others, okay, the disjunction is defined as in either of them or both are true. It is true, either it is true, otherwise it's false. Implication, this is logical implication as you would see. So if phi1 itself, the interpretation of phi1 is false, then the entire formula is true. Yeah, it is true if phi1 is false, interpretation of phi1 is false. It is otherwise it is it is true only if phi2 is values to true. So this is if and only if. So they'll have to have it's true if both phi1 and phi2 have the same truth value. Okay, and this one says exactly one of them has to, one of the sub-formulas will have to interpret to true. Any questions here? Okay. So this defines the semantics completely in the sense that for every formula, when you recursively apply these things, you will eventually, it's guaranteed to give for any given valuation for the proposition variables, either true or false. Yeah, so if the semantics assign to a formula phi in evaluation phi true, then we say that valuation sigma is a model, or in the that is a satisfying assignment for the formula. Okay. And we define these three logical concepts based on this existence of satisfying assignment. A formula phi is said to be valid if, that is, if it is all valuations of models. That is, for all valuations, the formula interprets to true. Okay. So that is all for all possible valuations, for all possible assignments to the variables in that formula, it should interpret to true. It is satisfiable if there, for some, if there exists a model for which the semantics assigns it to true. It is unsatisfiable if there exists, no model that can make the formula true. Yeah, so what I call as SAT checkers, okay, are algorithms to check satisfiability. Okay, so when we use this thing, checking satisfiability, meaning checking any one of these things, a formula, satisfiability of a formula. You can also observe that, see, validity and unsatisfiability are complementary. So if a formula phi is valid, the negation of that formula is unsatisfiable. And that's because of the way that we define the meaning of the negation, okay? That it is true if and only if the subformula is false, okay? Now, obviously, there is, okay, so we will talk, both about some way of, one, deduction system, okay, which has only a single inference rule to do it. So the SAT checker, usually satisfiability checkers are methods or algorithms to check satisfiability, okay? Now, since it's a propositional formula, there is already an algorithm that you probably would have, would have guessed, okay? See, our formulas are finite, which means although we start with a possible infinite set of propositional variables, assuming that our formulas are constructed from, formulas are finite. So given a valuation for the propositional variables that occur in the formula, there is a simple algorithm, okay? I call it the silly algorithm. What does it do? You can enumerate all valuations for the finite number of variables that appear in the formula, and then you can check. You can apply the rules here that I've specified inductively to get the truth assignment to the formula. It's pretty much like constructing a truth table, okay, that you would have seen for evaluating a Boolean function represented as a propositional formula, okay? Of course, that thing is not very efficient because you will have to, if the formula has n variables, you will have to perform 2 to the n valuations, but that is already there. So that's why propositional formula is given its finite nature of the domain over which the propositional variables range over. That is there is a formula, but what we are looking for are methods and deductive methods, as well as automatic methods that are efficient in practice, okay? So is this clear, okay? So this, what I say is the silly algorithm is just the, constructing the truth table for that. So I want to emphasize that satisfiability checking techniques are crucial verification backend for our verification methods. For example, in bounded model checking, what it does is it converts both the model, the program, into a formula, like you saw in the case of transition system, and the specification, the assertions to be verified, for example, the reachability of an error, that's what you want to check. That is also converted into checking a formula, okay, to be true, to be satisfiable or unsatisfiable. So usually if it is satisfiable, then if the formula that models, okay, encodes the reachability of error is satisfiable in that logic in which you model. Here we're talking about proposition logic. That means that model itself is a witness to an error. Okay, that's how model checking, or at least the symbolic model checking, works. And if it is unsatisfiable, then it is verified, because there cannot be any error model. Okay, any model that can satisfy it, and hence no errors. So that is one way to do. Or you can express the verification techniques as deriving a proof with invariance and so on. We will see that in some cases you need more sophisticated techniques, okay, especially for when you're using logic, predicate logic, okay, and you're talking about when the variables range over more sophisticated domains like numbers and integers and so on. So there you need to do a bit more sophisticated techniques, and so in general it can also be used as expressed as in terms of logical reasoning. Okay, so that's why it is very important that you understand these basic concepts of the logical concepts, as well as get some insight into the techniques for automating them. Any questions here? Introduce yourself. Okay.
Yeah. So I'm Siddhant,
okay.
And I was basically asking, like, so we know that SAT is NP hard. So in that case, SAT solvers work only on a specific class of Boolean formulas, or?
So let's hold on to that question, okay, about this, how hard, and obviously, yes, I will get to that. Boolean satisfiability, simple answer to the question is yes, they are NP. And all these model checking methods, which are built on top of these SAT checking methods, or at least are NP hard, okay, if not much harder than that as far as the complexity class is concerned, okay? But believe it, okay, the modern day SAT solvers work, although the worst case complexity is not necessarily, of course it is eventually a limiting factor, but they work. There are lots of tractable islands, okay, that a lot of the practical examples fit into, and that's why. And these modern day solvers, the SAT solvers, use a lot of heuristics, and when there are at the SAT level, there are lots of heuristics that they use, and there have been a lot of advances in the last 10 to 20 years, since early 2000, that has made SAT solvers, present-day SAT solvers, scalable, okay, to realistic systems. And then also various techniques that you can do at the model level, okay, in the way that you model or throw away, using what I call abstraction techniques at the model level to make the problem more tractable, okay? So maybe that's what, maybe I answered a little bit more long-windedly. Does that answer your question? So we will.
Yeah.
Yeah. Yeah. Yeah. So, SAT solvers, in general, you use normal forms for Boolean formulas, because you've heard of various normal forms, and the normal forms come in handy because they are ways to represent any Boolean function with a smaller set of some limited fixed set of Boolean operators, and they usually have special structures which come in handy to automate this decision problem. I keep talking about a decision problem. What I mean by decision problem is SAT checking problem is usually called. The Boolean, the decision problem, or a satisfiability problem, the problem of automatically checking satisfiability and satisfiability or validity of, in any logic is called the decision problem. Is a decision problem in that logic. Okay, so we will see. So, one such normal form is the conjunctive normal form. Okay, so which you, I'm sure, most of you would have heard, in which is every Boolean function is represented by a formula that uses use only disjunctions and conjunctions in a specific way, with negation appearing only at the leaves, at the atomic, at the leaves. Okay, so it's a formula, a preposition formula said to be in conjunctive normal form if it is a conjunction of a finite set of clauses, where every clause is a literal. It is a disjunction of literals, where a literal is positive, that is a prepositional variable, or it's a negation. Okay, that's a literal. So these things that are components of a clause are literals. Okay, are called literals, and these are each of these conjunct is called a clause. Okay, that is a conjunctive normal form. The dual of that is the disjunctive normal form, in which a formula is represented as a disjunction of finite disjunction of what are called cubes. Okay, cubes. A cube is a conjunction of finite set of literals. Okay, that's disjunctive normal forms. When you have, and there are other kinds of normal forms as well that people exploit, that are in practice to come up with efficient methods to decide to solve the decision problem. So, for example, there was this question by Saddam about the complexity of the Boolean satisfiability problem. So, if you have things in either in CNF or DNF, then some of those decision problems can be efficient. Okay, and some of them are in P. So, for example, if a formula is in CNF, then checking validity is linear. Okay. Linear in the size, in the number of clauses, the number of in the size of the formula. That is because CNF is a conjunction of clauses, and in order for that to be valid, that is to be true, no matter for all possible valuations, every conjunct has to be true for every possible valuations of the prepositional variables. And a clause can be valid, which is a disjunction of literals, is valid if and only if it has at least one literal in that appears both in positive as well as negative form. That is, the disjunction. A clause has to be a tautology. A tautology is, the valid. Okay, I'm sorry. Yeah, so it can only be so. Then what it requires is checking. For example, to check this, you will have to make one pass through the formula and check if every clause contains at least one literal in both its positive as well as negative form. Only then can it be valid. Okay, so that's why this can be checked very inefficiently. Checking satisfiability is NP. And the intuition is, you'll see, you'll have to check that no two pair, there's some subset of these clauses cannot be satisfied simultaneously for, unsat. Okay. So, satisfiability is you will have to find one of the evaluations. And sometimes you may end up having to look at all subsets of the formulas the clauses, and that's why it is NP. So unsat is co-NP because it is the complement of sat. So if the formula is already in DNF, then checking unsatisfiability is linear, and so the validity checking becomes hard. Okay. So, but for an arbitrary Boolean formula, yeah, so you can, yes. So that's why. So in general, since for checking for arbitrary Boolean formula, you will have to get them into one of these CNF or DNF. So this, that itself may have a blow up. Okay. So in general, that's why it is said to be NP. Okay. Okay. So, I mean, of course, I haven't given you a proof of these things, but that is not. You can find that in literature, and you can even do a wiki, and then usually it is one standard proof is to reduce that to a clique problem. Okay, finding a in graph. Okay, and that is one way to show that it is NP. Okay, so how do we do reasoning in propositional logic? Any questions up to this point? Okay, any questions about the notion of satisfiability, unsatisfiability, validity, etc. So now we are getting the next part is to look at some techniques for doing reasoning. Okay, in propositional logic and the techniques for automating it. Okay, we will not talk about, some of the, the decision procedures, automated decision procedures early on, they were based on a way of representing, a canonical way of representing Boolean propositional formulas or Boolean functions, okay, called binary decision diagrams. Okay, so until SAT solvers became, until like early 2001 specifically, this method of BDDs were the go-to method to decide, to efficiently decide, at least when it worked, in a propositional formulas. But there were several breakthroughs in SAT solving techniques in the first decade of 2000, when SAT solvers became, very efficient for very large class of formulas that, BDDs are, mostly, almost all verification, especially software verification tools most of them use SAT solvers as their backend. So I only briefly mentioned BDDs. The BDDs as a decision procedure still work pretty well for hardware applications. Therefore, they are still very much used there. But for software application, it is mostly SAT solvers. And so we'll spend more time on SAT solving and understanding. And that too only for a couple of things. As I told you, I mean, our areas will mostly in the course be using SAT solvers as black boxes. It's only in the first few lectures, the next few lectures, that we'll be talking anything and that I will be covering about SAT solvers only in the next few lectures. Okay. So what is this? It's a data structure for representing a formula in propositional logic. It's a compressed decision tree, or it can also be viewed as an automata. Okay. So paths to, there is a root node and there are several paths to terminal nodes. And each of those paths to terminal nodes starting from the root correspond to a valuation of the formula. Okay. So, and the terminal nodes represent either 1 or 0 because the valuations for the formula has to be 1 or 0. So these are called more specifically called reduced order binary decision diagrams. Okay, and they are there is a restriction on the thing that in each path, in every path leading from the root to the leaf, that the variables have to appear in a specific, in a fixed order. Okay, so with that assumption, and then there are certain things there cannot be any, it has to be in a merged fashion. It's a graph rather than a tree. So with those two assumptions, that it is reduced and it is ordered in the sense they use the variables appear in the same order, will ensure that these are canonical representations for a formula, in the sense they are unique. Okay, in every function, Boolean function has a unique representation in this things. For example, this is Boolean. This is a representation for which function? Okay, so for example, it should be read as if A is 1, the solid edges are 1, and the bottom, the dashed edges, 0. For if A is 1, 1, then it is 0. Okay. If A is 1, if A is 1, if A and B are 1, it is 0, regardless of C. If A is 1 and B is 0, then it is 0, and so on. Okay, so that's how it is. It should be read. Okay, so then every function has a unique representation. Okay, so once this is constructed, then since it's a unique representation, if a formula is valid, then its unique representation will be the node 1, and if it is unsatisfiable, then it will be 0. Otherwise, it will be something else, and you could then once you construct it, then that's what, as I said, ROBDDs are canonical, and for any given ordering, they're canonical. But once they're constructed, then the decision problem can be, decision checking is just constant. Okay, but the catch is that there might be some functions, Boolean functions, for which every possible ordering. So the size of these canonical representation of these BDDs for any given function is extremely sensitive to the order, the variable ordering in which. So in this case, for example, the variables are ordered in is A less than B less than C. Okay, so you can see in every path A appears before B, and B itself appears before C. Okay, so whatever Boolean function that this is representing to, there can be other canonical representations for other orderings of A, B, and C. So the size of that is very sensitive. It is a function of the variable ordering that you choose. Okay, so if you happen to choose the right kind of ordering, then these BDDs representation are not only canonical, but they can be very compact for a Boolean function. Therefore, once you construct them, then all the satisfiability checking is easy. But you saw that the decision problems NP and NP hard. So what's the catch? So there are some functions, turns out that there are some functions for which no matter what variable ordering that you choose, you can never have a compact representation in terms of BDDs. So the problem here is still quite effective if you have a way of choosing the right kind of ordering, but a priori determining what ordering will give you the best possible sized BDD is itself NP. But there are various heuristics that people have developed to determine based on certain structural property for your Boolean functions that makes it possible. I mean, you can guess these are heuristics, guess the orderings, and they seem to work quite well for a lot of functions that you encounter in practice. And this BDDs, they can scale up to several hundreds of variables, even thousands of variables, as long as your formulas have hundreds or low thousands of variables. Then these techniques are quite effective. Okay, so that's all that I'll mention about BDDs. Okay, so but you should be aware that there are this method wherein this is kind of memory intensive, in the sense you have to first construct. Okay, and once you construct, the decision problem can all be decided in constant time. And also, if there are two BDDs applying these various logical operations on two formulas that are already represented as BDDs, are quite efficient. They're actually linear or at most quadratic in the size of the two BDDs, and that's why these methods are quite efficient when they work in practice. And there is one open source implementation, which is quite stable, and the thing called that is developed at Colorado University, called the CUDDD package, which one can experiment with. But in this course, we will not be looking at BDD methods, but mostly, as I said, we'll be concentrating on SAT solving for our purposes. Any questions here? Okay, so I'll get to start talking about SAT solvers. So what are SAT solvers? Tools for deciding, okay, the satisfiability of a formula that is expressed in CNF form. Okay, all SAT solvers, even to this day, they assume that the input formula that it gets is already in CNF, and then it not only besides checking if it is satisfiable or not. If it is satisfiable, it checks if it is satisfiable. If not, it says it's unsatisfiable. When it is satisfiable, it produces a model that is a satisfying assignment for the variables in the formula. Yeah, so there are, this is sometimes, there are complete solvers and sometimes there are incomplete solvers, but that's not important. So, modern day solvers, they easily scale up to millions of variables, formulas that have millions of variables, and in sometimes even tens of millions of variables, okay, for specific things, and tens of millions of clauses, okay. You can see how these things, we will see 2 or 3 breakthroughs that happened in the first, in the early, in the first couple of decades, in the last 20 years, that allowed this scaling to happen. And these are SAT solvers now these days are the key components of most automatic software verification systems. There are lots of them, and there is a conference in which, as part of which, there is competition that happens every year, and there are several dozens of SAT solvers that get entered in that competition, and every year they give a gold, silver, and bronze medals for the top 3 SAT solvers, indicating that there is the engineering and the basic research. There's a lot of research still going on in this area of SAT solving. So Microsoft, we will be, at least in this course, you'll be using Z3 as a demonstrating tool. By the way, your Thursday tutorial will be devoted to giving a demo. Diganta will be giving you a demo of a Z3. That is a SAT solver, by Microsoft, and that's also very one of the top 3 or 5 SAT solvers that is there in the market. And he will also illustrate examples of how one can use SAT solvers to model problems, including like transition systems and so on. So that's the first exercise that would be of interest for us. So please do attend, and we will be getting some assignments on using SAT solvers, as well as CBMC later in the course. And I think you should make it. I also will like to, if you have any questions about the lectures and so on, you can use the tutorials to ask them, and maybe Diganta will be able to explain it. Even if not, those questions can then be discussed, and even if they're not answered, they can be compiled to have a discussion during the lecture. So that's tutorial is not only to get exposed and hands-on experience on these tools, as well as for you to raise questions about what I cover in the class. Okay, so that's the agenda for this Thursday's tutorial. Okay, so one question that I thought someone would ask at this time: if SAT solvers, they take only CNF formulas in CNF, isn't there already trouble in the sense, if the formula or the Boolean function, if the formula you start out with is not in CNF, okay, then just the conversion process of your formula, which might be using lots of Boolean, other Boolean functions, when the conversion, because they could be a blow up in the conversion. So even before you enter your formula, which has to be in CNF to a SAT solver, won't there be some blow up? Now, how do you overcome this problem? Okay, and that is where there is something called a way to transform your formulas that may have other Boolean connectives besides what CNF formula restricts it to. So that besides the conjunction and OR. So if you have a formula that uses other Boolean connectives, so that's what I call as a circuit, transforming such a formula into a CNF formula. Because when you try to do this, you'll have to use the De Morgan's laws and distribute and over or, etc., depending upon how these Boolean connectors are defined in terms of or and that can cause a blow up in the number of clauses that you eventually produce. But there is a technique to transform such Boolean formulas that use other Boolean connectives without actually by adding new variables to denote the output of the intermediate output of the Boolean functions, such that the resulting conversion, the resulting formula is satisfiable every time the original formula is satisfiable. That's what equisatisfiable means, and without causing an exponential blow up, okay, in the number of clauses. Okay. Now, I'm not going to get into this. I will have Diganta explain to you this transformation in one of his tutorials. Okay, the details of that will be there. And so this is something, even if sometimes the tools, SAT solvers themselves, they do accept you will see almost all modern day SAT solvers do accept any arbitrary formula. Okay, although internally, the engines, the algorithms that work on, they have, convert them into CNF. Okay, and when they do that, they usually use this transformation, which is due to a guy called Seitan, and so there's some details of what this transformation is and how it overcomes this thing in a structured way. But of course, it will introduce a set of new variables, but the number of variables that it introduces is linear in the number of connectives that are actually used in the formula. Okay, so what it prevents is an exponential blow up in the number of clauses. So this will be, you can see this if you attend one of the tutorials. Okay, so what is, first I will introduce to you something called a resolution, an inference rule called resolution. See, I mean, of course, I said the SAT solvers actually are automatic methods. And the logical, when you have logical reasoning, they usually, as I said, the proofs are developed within proposition logic in terms of inference rules. There are lots of deductive systems. Some of you who have taken formal logic would have seen natural deduction, sequent calculus. These are set of inference rules. That's what I call as deductive system, in which you could develop a proof of checking validity, proof of establishing validity of a given formula as a proof, which is where a proof is a sequence of inference rules that are inference rules drawn from the deductive system. Okay, but there is one deductive system called resolution system, in which there is almost a single inference rule called the resolution inference rule. Okay, and that's what I'm going to discuss today, because the resolution inference rule happens to be the basis for the algorithm, even to this day, with all the modern advances that are built into SAT solvers and the various engineering and so on. If you rip all the engineering and the heuristics out, at the core, what SAT solvers, present-day SAT solvers, use are algorithms that use this resolution inference rule. Therefore, it is, maybe some of you have seen a resolution inference rule. How many of you know about resolution here? Is there anybody here? Yes? No? Is that a no? Are you guys still there?
No. Yeah, I think that's a no.
Okay. Okay, so then case, this will be something. So I will briefly introduce you resolution thing and how to do proofs using this, just for interest's sake. And then I'll talk about the techniques of SAT solvers. I mean, so when I talk about SAT solvers in the way that it is presented, you may not even recognize the resolution is used, but you will see that resolution is the basis, okay? Basis for SAT checker, okay? Of course, SAT checker is more than just resolution, but yeah. So what is resolution? Okay, resolution inference rule, like I said, an inference rule is defined as, using the vertical, an horizontal line. There's some, you should read this as, if you have a formula in CNF, okay, which has, okay, there are two clauses, where A is a set of, disjunction of literals with okay, two clauses, A or X, and with at least one variable that appears with different polarity. Okay, it appears with positive polarity in one of the clause and with a negative polarity in the other clause. If you have these two clauses, then you can replace that with a clause. You can eliminate X and not X in the two clauses. So here A and B denote whole disjunction of literals. Okay. So what it says is that if the conjunction of these two clauses that are above the line is satisfiable, it is satisfiable if and only if the clause that you get by just taking the union of A and B, A or B, this is satisfiable. So if the original is unsatisfiable, it is equisatisfiable. So if the original is satisfiable, so is the clause in the denominator of the inference rule. And if the original is unsatisfiable, so is the thing. So that's what it means. And you can see this because if you use distributivity laws over the conjunction of these two literals, you actually end up saying that you can reduce that to A or B, okay? And you can get rid of X and not X. You can do that exercise yourself. And this is what resolution principle says, that if you have these two formula, two clauses with one literal appearing in the opposing polarity, then you can merge those two things and then get a new clause. And you can add this clause because this is equisatisfiable. It's actually an implication of that thing, as I've shown here. Therefore, you can actually add that to your original set of clauses without changing its satisfiability status. Okay, and what resolution proof does is it is just it says that you can keep applying these inference rules until you get a contradiction or you can't apply them anymore. Okay, more generally. So here is, okay, that's kind of just introduction. By the way, this resolution principle historically was introduced by Robinson in 1965. So what it says is, if C1 and C2, let C1 and C2 be two non-empty clauses, it's a more detailed description of the resolution inference rule, okay? And if you have two clauses of this kind, okay, a set of literals and another set of literals, with one literal, here in this case C, appearing in with opposite polarity, then you get these things. So R is said to be, you get by taking all the other literals, taking the union of all the other literals in C1 and C2. Okay, and what it says is that, and then there is another rule as well, okay, one that derives a contradiction, that if you have two unit clauses, a unit clause is a clause with a singleton literal. So if you have two unit clauses with literals in opposing polarity, then that is a contradiction, because you cannot, that is not satisfiable, correct? That is actually unsatisfiable, and therefore that is thing, and it results in an empty clause. An empty clause is the same as having reached a contradiction. Okay, so and then there is sometimes the application of this resolution can result in a true as well, a tautology. So for example, if these are the two clauses, when you resolve using B and B hat, then you will end up getting the union of A and A bar, negation of A, which is a tautology, and therefore that can reduce to true as well. These are two kind of special cases of the application of resolution. Any questions here? Okay. Yeah. So what is the theorem? What is the soundness? This is also called the soundness theorem of resolution. If you have two clauses, by the way, this resolution inference is called binary resolution because it is applicable to conjunction of two clauses. If you have a formula with two clauses, C1 and C2 with the above structure, and you apply the resolution inference rule to get a resolvent, which is a new clause R, then it says that C1 and C2 is equally satisfiable with R, which means that whenever C1 and C2 is satisfiable, so is R, and if that is one is unsatisfiable, and so is the other. Based on this, one of the early methods of automatic methods was based on this resolution principle, and that algorithm, or you may want to call a strategy, because that was presented as developing resolution proofs, but it was really kind of an algorithm to decide the satisfiability of formulas in a conjunctive normal form. It was actually an algorithm that was called Davis-Putnam strategy due to these two logicians. Okay. So what it basically does is, given a CNF formula phi, you repeatedly apply this resolution until you either derive a contradiction, in which case you can conclude that it is unsatisfiable, or you have no new resolvents, okay, implied clauses are generated, in which case it is, you can conclude that it is satisfiable. Okay, in other words, so a naive algorithm that can be used for automatically deciding Boolean satisfiability is the following. So input is a formula in CNF, and you select a pair with a pair of clauses in the original set of clauses. I keep saying set of clauses, okay, because the original formula is a disjunction of clauses. That is sometimes I refer to as a set of clause, okay. The set of clause means the original formula is just disjunction of those clauses. You select a pair with complementary literals, and you derive a new clause by a resolution. In that, if there are repeated literals, then you may, or if it reduces to true, then you just get rid of it, which is possible, like I pointed out in this case. Okay? What happens? Yeah. Or if there are, sometimes you can, when you take the union of the rest of the literals in the two things, you can get repeated literals, and you may, it's just saying you can remove repeated literals because they are redundant. And if discard if the clause is valid, that is, if it reduces to true. Otherwise, you add the clause to your original set of clauses, and you keep repeating this until you either get a contradiction. That is, you derive an empty clause, in which case you can declare it unsaid. And if no resolution is not applicable anymore, then you can declare it is sat. So I will end this lecture by showing you a couple of examples. Okay. Here's a formula. So I'm using plus to denote disjunction and dot to denote conjunction. So this formula, as you can see, eventually it is insensible. So this is a clause A plus B, A or B, and A or B not. So there is scope for applying resolution, because B, the variable B, appears in opposing polarity in the first two clauses. So if we resolve that at the variable B, that's usually that's called a pivot variable, the variable B that appears with opposing polarity that you choose to apply the resolution. That's called a pivot variable. So with the pivot variable B, then you get A, because you eliminate that and you take the union of the rest of the literals. In this case, both have A. Therefore, that gives rise to A. Similarly, C appears in opposing polarity here. So you can resolve these two literals with C. Then you get not of A. And that gives rise to contradiction. Therefore, the original set of clause formula is unsatisfiable. Okay. Any questions here? Okay. As you can see, I mean, I want to make an observation. See, if you were using the naive method, okay, where you would construct the truth table for the thing, then you would have, in this case, since there are three variables, you have to check the valuation for 2 to the n, 8 such assignments, right? So, in this case, there are three variables. But as you can see here, all you needed was just 3 resolution steps to get a contradiction. Okay, so sometimes your resolution proofs can be very compact, okay, in the sense of the number of resolution steps that you will have to do. So this is what I call as a proof, because after all, this is just repeated application of that resolution inference rules. Okay, this is an example of getting the thing of so, and I will stop here. Okay, so here is an example of where that shows satisfiability. So this formula, so you can resolve on the using the first 2 clauses on C to get this resolvent, A plus B and not F. And with this new, you can resolve the new clause with one of the original clauses here. Okay, and this is the only original clause on B to get this. After that, there are no more resolutions possible. Okay, so you will have to use both the original clauses as well as consider all the new clauses in order to, you will have to save them in order to check if there are no more, if no more resolution is available. So in this case, it means that it is satisfiable since you are not able to generate any new resolution steps, that ended, and therefore, right, as you can see, any satisfying any assignment that makes one of these literals true is a satisfying assignment to the original formula. Okay, so I'll end here, except to take questions. Any questions? We'll continue with the same, with SAT, discussing SAT solvers in the next class. Any questions? Okay, so please do, if you have any doubts after you listen to the video or the thing, if you get any doubts, please post them during tutorial or in the next class. Okay, okay, good. If you have more questions, I will stop sharing. I will end.